Hey guys, here's a look at how to do related rates. So if I give you a revenue function, the idea is you have to use implicit differentiation, which I also loaded some videos on. It's its own entity. It's not too difficult, but using implicit differentiation, we can solve these related rate problems. So the idea is to do it's with respect to time. We're going to see how revenue and changes and the number of units that are implied in that x is the number of units, how x number of units changes with respect to time. So if I keep going with this, the derivative of both sides, you do the left and then you do the right. The left is nice, derivative of r is just dr dt. That means the rate of change of revenue with respect to time. And on the right, we're taking of that function with x in it. Remember, x is number of units. And we take that derivative. This is where, right now you're seeing what the derivative is as we've always done it. So derivative of 100x is just 100, and the derivative of 0.002 x squared is just 0.001 x squared is 0.002 x. But what's changed is with implicit differentiation is that if you took the derivative of an x, or any variable for that matter, you have to put that dx dt after it, or whatever the variable is in this case. That's just because we did x's. So there's the full derivative implicitly. You're hearing a lot of my family in the background there. So this equation is what we call, it relates the rates of x and r as time changes. So that's what a related rates problem is you're looking at multiple rates of change because you have multiple variables. When you took the derivative of, we're going to see how each of them change and how they affect one another. So we're going to ask, usually actually the hard part is not taking the derivative. You can see above that's not too difficult. But it's actually coming up with the equation you do take the derivative of, what you want to find out, like what your question's shooting for. Well, I'll make that pretty direct for our problem's sake, so you're actually getting to the meat and potatoes of just doing the derivative piece. And so here's kind of a question that I might ask. And that type of question is, it's an example, and most of them are pretty similar to that. So if you have revenue is modeled by that function that we had on the left there, that 100x. And you can create revenue from x times the price, x times the number of units, x being the number of units times the price you sell them at, and price is a function itself. So we've done that in the past, but right now I'm just handing you revenue as is. So if we go from producing 2,000 units per week to 2,200 units per week, that is increasing production 200 units per week, we want to know how revenue changes. So these are really interesting problems because you're going to increase production and you're going to see how that changes revenue and at what rate that's changing given that increase in production, which is pretty informative. So here's how it's set up. So we have the derivative. All you have to do is once you have the derivative, you take these givens, which you're always going to be given, by the way. You're going to be given a certain number of units, and you're going to be given a rate. So you're guaranteed to be given some type of units, some x value, an input value, and at least one rate to work with. You just substitute those values in and solve. And so the next piece here is subbing in those values. So I'll take that same equation. We'll put in the values in parentheses. You see 2,000 and 200 in their respective spots. I'll label them here. But next is you just calculate that. We get $19,200 per week increase in revenue from increasing production 200 units per week. So that's informative. That increases revenue. What we haven't accommodated for when we're just talking revenue is how much that means in costs. Like what's going on with costs. Maybe the costs are actually more than that. More increase in costs versus a lower increase in revenue means our profits would be going down. So this is just one particular measure. Good to see revenue go up, but we should probably look at cost if we're going to continue this problem. And that's about it. Now let's do an example here from a practice test that I'm going to give you guys as a review for the test coming up. So here is, I've given you D over the little d. Actually, that could be a little p. That means price or demand, either one. I've circled it in red there. And then you can see it below in the big P profit function. I've circled, I pointed it out in the parentheses there, that's price, and X units, so that's our revenue chunk, that left-hand side of the profit function. Then we, of course, so there it is, revenue. Now, next is the cost function, which will be given in some form. I've pointed to that to the right-hand side of my profit function. It's in green there. And so there's that cost function. So now, if you take a look at this function, full profit function down on the bottom, that's the one we're interested in because our question is find the rate of change of profit when monthly sales are 700 units and the rate of change of sales is 500 units or 50 units per month. So when I say find the rate of change of profit, that means you got to find the profit function to take the derivative of, and then plug in the rates, the given rates, and the given units they're offered in the problem. They have to be there, and then when you're done substituting, one of the rates that we're going to solve for will be as a variable by itself, and we can solve for it. So that's what happens here. So with this nice built profit function, what I'm going to do is simplify it a little bit. So you see there I've distributed. Now I'm going to combine those like terms, 1700x and 240x. And then if I take the derivative of it, so there's that 1940 dx dt. The big key is after taking the derivative of functions as we know, negative 0.016x squared is negative 0.032x, you have to include that dx dt afterward. That's really the only difference in implicit differentiation. And then 1940 comes from the derivative of the x term, and you put a dx dt after it. So anything you actually take the derivative of, you have to do it as you would, as we have all along, but then add the dx dt at the end. So there's the nice derivative. Now we're going to sub in the values we know. 700 for x, dx dt is 50. Drop those in there. And then we're home free. We substitute those values. You can see them there. Calculate. And things look pretty good. I think there's going to be a nice profit change here. $95,880 per week increase in profit by change of sales of 50 units per month from the current rate of 700 units per month. So I'd say that's a pretty good deal. Hope that helps. There'll be another one coming as well.